Hey, hi everyone. I hope everyone is doing well. So today's video is going to be basically discussing about another data structure type called heap. So remember, we have covered trees, we have covered lists, we've covered list and operations, right? So today we are going to discuss about heaps. What are heaps? Heaps are basically data structures that satisfy some, property, right? And what is that property? So basically, the parent node, right, is always greater than or less than its child node, right? Uh, Heap can be used to implement efficient, let's say, algorithms for a variety of tasks, right? Like sorting, priority queues, and the shortest paths. Now, I think in this video, I will try to give you probably beginner to medium stage uh, concepts related to heap. There are still some concepts that I feel like might need another video, but do leave in comments. I think if you feel like those concepts have to be discussed from an interview preparation perspective. I'll probably put it in some way to kind of highlight. I think how those algorithms are implemented, but I think for the purpose of this videos, by the end of this video, you should be able to like understand what are the data structures that satisfy the heap properties, what are the different types of heaps, their examples, implementation, advantages, disadvantages, right? So that's what we're going to cover in this video, right? So starting off with, I think what are the different types of heaps, right? So there are basically minimum heaps, maximum heaps, right? There are also binary heaps and D-ary heaps. So what do you mean by a minimum heap? So basically, a minimum heap is a complete binary tree, and it is ordered in such a way that the value of each node is less than or equal to the value of its child nodes, right? So let's look at this, right? For example, here you look, right? It is an ordered heap, first of all. The value of each node, right? So for example, if I look at this node, right, the top node, which is the root node, is it less than or equal to the value of its child node? Yes, it's less than both 2 and 5, correct? If I look at 3 and 4 and 2, 2 is again less than both 3 and 4. And if I look at 5, it is definitely less than both 6 and 7, right? So that is an implementation, or like what do you call like a minimum heap. Similarly, there is the concept of maximum heap, a type of heap. What is it that a maximum heap has? So again, a complete binary tree, and that is obviously ordered, and in a way where each node is greater than or equal to the value of its child node. So here, for example, if you look at 10, right? So 10 is basically greater than both 4 and 7. If I look at 4, 4 is also greater than both 2 and 3. If I look at 7, 7 is also greater than both 5 and 6, right? So it's an arrangement and an ordering way in which, you when you reach a certain node, you realize, and if it is a parent node, right, you'll always find this property to be satisfied, correct? There are binary heaps. That is obviously, both of these combined, you can call it like binary heaps. So not necessarily a type, but binary heaps are again a special type of, like, I would say, heaps type, and you can have the parent node as either greater than or equal to both the child node, or it can be a less than or equal to kind of a structure, right? Which is basically what min and max heaps are. You can also do an implementation of D-ary heaps. And what are D-ary heaps? So D-ary heaps are nothing but you are not limited to just two, nodes, or two max nodes, right? So here you see, for example, 2 and 3 and 5 and 6, for example, max nodes, the child node that you could have had is 2, right? Here, it's a generalization of a binary heap to d children per node. So I have more than two nodes, right? I have majority of the nodes as not being limited to only two, right? So that is a D-ary heap. Now, coming to, I think, the use cases of heap, right? Where are heaps actually used, right? So there are a lot of sorting mechanisms where heaps are pretty useful. And heap sorting, right, uh, basically looks at heap as an item, and then uses sorting algorithms, right? So a heap sort is a sort of an implementation where you are sorting, creating a sorting algorithm, right, that uses heap as an object, a data structure object, right, to sort a list of items, correct? Um, how do you implement it? I mean, a rough way of implementation would be you obviously first build a heap, right? And then let's say you remove the largest or maybe the smallest item only. And then you either place it at the beginning or the end of the sorted list. So that is basically a heap sort. There is also a priority queue, which is basically an similar, like, data structure that is a heap that allows items to be inserted or removed in a way where the highest and the lowest priority items are always at the front of the queue, right? Now, do leave a comment if you want to see the implementation of it. But I think from an interview perspective, priority queues, yes, if you are going for software engineering interviews, I'm pretty sure you'll be grilled on this. If you're looking at, I think, only product management interviews, you should know about these, I think, different kind of algorithms, not necessarily the implementation. Implementation part is where the software engineers are obviously supposed to be knowing these, right? So you should know that, okay, through heaps you can basically implement a priority queue, correct? Um, Now coming to the advantages, right? So advantages wise, I think obviously heaps as data structure offer efficient sorting. There is a time complexity of n log n, and which is the worst case. What is a time complexity? I think I haven't covered this concept, but understand time complexity as uh, the minimum time, the maximum time, the average time that it takes to traverse the, let's say, a data structure, right? That is what is called as a time complexity. If you were to find an element, let's say in a list, in a tree, in a heap, in a graph, what is the time that it will take, right? And there will be different cases, right? You can have the worst case, you can have the best case, you can have an average case, right? So time complexities are calculated on these three parameters. I can do a separate video on it, and then the reason I am not covering this is because when we touch advanced algorithms, there's going to be a discussion on time complexity. But for now, understand that for heaps, time taken to sort an array of, let's say, n elements grows logarithmically with the size of the array, which is definitely advantageous in some cases, right? Um, it offers flexibility, heap, right? Because you can include integers, floating point numbers, strings, and even custom objects, right? Heaps are also very adaptive. So from small sample data sets to large data sets, you can use you can use heaps to sort arrays, right, of different sizes. um, it is adaptive, meaning that it can adjust its behavior based on the size of the array that is being sorted. Um, I think on the memory usage front, yes, it uses small amount of memory to sort an array, especially compared to, let's say, maybe the other sorting algorithms. The one on top of my mind are probably like the merge sort, where you're merging elements, right, and then replacing those with a final this thing, an element. Compared to that, obviously, heap sorts use small amount of memory. Do you have to remember these? See, I think memory discussions will definitely come, and when you're going to level of details of implementation of certain kind of applications, right? So you can probably point out this as the one element where you say that, okay, it uses, let's say, less memory as compared to maybe trees, right, or as compared to maybe lists, correct? So efficient for sorting larger data sets, yes, I mean, it is one of the advantages, because it needs to compare the elements that are close to each other in the heap, right? So that is basically the efficiency, that is where the efficiency comes from. And it is definitely very useful for sorting very large data sets that are too large to fit in the memory. It is easy to parallelize, which means that to sort large data set, it's easy to implement in a distributed environment. Now, coming to obviously the disadvantages, right? It is, I mean, going to offer some bit of, I think, disadvantages when it comes to search. And why is that? Because so heaps basically allow for, like, I would say, efficient insertion and deletion of elements. But it can be slow for the search. And why it is slow for the search is because you're trying to find a specific element. So one is that if it is not sorted, then you have to sort. And even if it is partially sorted, right? What if the element is basically located at the bottom of the heap, right? So not probably like the best use case when implementing search, right? You don't use heaps a lot when you're trying to design, let's say, a search system, correct? Let's say you're bringing in a search functionality in your application, you probably not going to go with heaps, right? Lack of order persistence. So basically, there's no guarantee to maintain the order of the elements in heaps, right? The order elements are being constantly moved around to maintain the heap property, right? So, for example, you come back to this example, right? Now, this minimum heap basically has a property, correct? That property is that the parent node is the lesser of 2 and 5, right? So, one is obviously less than 2 and 5. Now, imagine if you were to delete this 2, then you have to rearrange every parent node, every child node, right? So if you remove 2, for example, you will have to first do a comparison of what is left, 3 and 4. So if you decide to make 3 as a parent node, then you take 3 here, right? Because 3 has to be lesser than 4, correct? You can't take 4. So that is the computation that will come into picture, correct? So that's just an example, right? So that is what it means, that elements are being constantly moved around to maintain the heap property. Any heap will have a specific property, and that you have to maintain when the elements are being moved around. And this is definitely going to be a problem if your application requires a specific order to be maintained, correct? So heap, there is no order persistence, correct? It is inefficient, obviously, for certain operations. It is definitely efficient for insertion and deletion, but it is, as I mentioned, right? It's slow in search, which means that finding a minimum or a maximum element, it's not the best choice of data structure, right? Also, it is obviously very sensitive to the input, because if the data is already sorted or nearly sorted, then let's say this is kind of a sorted algorithm, right? A sorted data structure, the heap is still going to perform its operation to identify and verify that the properties of the heap are there, right? Which means that if your input data is already sorted or nearly sorted, you are still going to spend time. You're still going to spend time to verify whether the heap properties are present or not present, right? So, which means you are spending time, right? So there are definitely these disadvantages that you should bring up when saying, like, for example, whether a heap is a good tree, heap is a good data structure or a tree, right? When we cover, I think the examples after, let's say, completing most of the data structures, I'm going to bring this up, and we are going to see how this is useful in a system design interview, right? So do leave a comment. I think if you feel a certain data structure is more beneficial in certain scenarios, for example, search implementation, or if you feel, for example, let's say sorting, right, a catalog sorting, for example, right, or if you feel price sorting algorithms, right, can be implemented, then think about what data structures could be more useful, right? So for example, if you are sorting a price SKU, right? So price SKUs basically, you are constantly changing the price, right? You're constantly, let's say you have price of 100 items, some items are added, some items are moved, then you keep on, like, changing the order, right? Then that's obviously not going to be a very good use case for for using heaps, right? So think of, I think, the practical application, think of the properties that the heap offer, and then combine both of those. Then you will know whether heap is actually a good data structure to use or not. Now, coming to the implementation in Python, right? So HeapQ basically provides a lot of functionality. So HeapQ, you can obviously import HeapQ. However, a caveat is that it does not provide the complete implementation. So when you want to check, whether the heap is empty, it's not going to be useful, and it obviously doesn't allow you to iterate over elements in the heap, right? So that's some drawback. So you might have to do your own implementation if you want to iterate over the element. But having these limitations, it's still a very useful, like I would say, library obviously to know about. You can read about, I think, this in the Python 3 documentation as well, but I have tried to cover some examples. So for example, like your standard, heap queue is there. You have an array, then you basically have some elements, and then you basically heapify that list, right? Then the created heap, for example, right? This is what the created heap is, right? Now, let's say you want to remove the largest element in the heap, right? So you use a heap pop operation, which removes the largest number, which is 6, right? Suppose in the same case, for example, you wanted to actually add a new element to the list, right? So you can add a new element to the list by using an operation called heap push, right? You mention the list, then you mention the element, and then you create a heap, right? And then you test it out, and you'll see that 7, for example, is your element, right? That is added to the list, correct? So um, I hope, I think this video basically gave you a good understanding of what are heaps, what are the different types of heap, the advantages, the disadvantages, implementation in Python. Of course, it does not stop here, because there are a lot of, I think, algorithms, that can benefit from using heap as data structures. Uh, and I think from an interview perspective, specifically, if you're focusing on software engineering, this is by no means a complete like video that will take care of all your questions on heap. So do leave a comment. I can do an advanced video on this, just like we did for advanced list operation. Can cover it in another video, but for now I think this should mostly suffice, I think, for discussions on system design and product management interviews. So until next time, please do like and subscribe to my channel, and please be on the lookout for more content.